Hello and welcome to this video for Chemistry 30 in the Equilibrium Acid-Base unit. In this lesson, we're going to look at calculating the POH or the pH, but when we have a basic compound. So in the last video, we looked at calculating pH for acids. Now this chart again is in the data booklet. Everything on the left are the hydrogen donating compounds, which are acids. Everything on the right are bases, okay? So you'll notice that your bases are anions, negatively charged ions, and ammonia, NH3, okay? Now why this is important is because you have to first figure out what type of compound you have to know what type of ions you have. So if you have an acid, you have hydronium ions. If it's a strong acid, one of the top 6, then the hydronium ions is the concentration of the strong acid. But if it's one of these bottom acids here, these weaker ones, then you have to use square root Ka times the concentration of a weak acid. Well, bases are similar. The bases are strongest at the bottom, and in fact, only ionic hydroxides are strong bases. So things like sodium hydroxide, calcium hydroxide, okay? Only ionic hydroxides are strong bases, and the concentration of hydroxide ions now, because we are dealing with bases, so we have hydroxide ions, is X times the concentration of the strong base. X is the number of hydroxide ions in the compound, and we'll do some examples with that. Now, every other compound on the right-hand side above hydroxide is a weak base, with the exception of the conjugate bases of the strong acids. They're weaker than water. They're higher up than water. So that means that they're so weak that they're essentially neutral. So if you have the chloride ion, it's nothing. Okay, but if you have the sulfate ion is down here, it is a weak base. Okay, now to find the concentration of hydroxide ions, you take the square root of Kb times the concentration of the weak base. Problem though, only Ka values are given in the data booklet, not Kb values. So how do we find those? They come from taking the ionization constant of water, Kw, which is 1.0 times 10 to the negative 14, and dividing by the Ka of the conjugate acid of that base. So again, if I'm looking at sulfate ion, the conjugate acid of it is HSO4 negative 1. Its Ka is 1.0 times 10 to the negative 2. We'll go through the notes explaining all this in detail, but this is an overview of, again, what ions you have depending on what compound you have, and then again, how to calculate those ions. So strong bases, again, are all ionic hydroxides. They react 100%, and they don't necessarily react, they dissociate. Strong bases are always, like I said, ionic hydroxides, like sodium hydroxide or calcium hydroxide. They are a compound with hydroxide ions. When you put those in water, they just dissociate into their ions, okay? And so the concentration of the hydroxide ions, this is kind of a shortcut. Rather than doing what we did in Chem 20, which was concentration wanted equals concentration given times wanted over given. This kind of does that really quickly for you. So I'm starting with what is my compound. It is a base because it's an ionic hydroxide, and not only that, it is a strong base because it's an ionic hydroxide. Okay, so to find the hydroxide ions, because again I have a base, I'm going to take the number 2 and multiply by the concentration of the base in the question, 0.0600. The 2 again is the number of hydroxide ions in the compound. That's what the subscript there is telling you. There's 2 hydroxides. So the concentration of the hydroxide ion is 0.120 moles per liter. Now I'm going to take the negative log of that answer, but when I take the negative log of that answer, it's important to note that you are not getting an answer on the pH scale because these are hydroxide ions. You're getting a number on the pOH scale. Okay, so 0.06 times 2, negative log of that answer, and you can put it in your calculator exactly like that. you're going to get a pOH of 0.9208, so on. And the question is asking for pH. So I can find the pH by 14 minus the answer I just got. And again, put it in your calculator exactly like that. I get an answer of 13.07918, so on. Remember our sig-dig rules for pH. I look at the total sig-digs in my concentration or mass or volume, whatever I have. Leading zeros don't count, so there's 3 sig-digs or 3 total digits in the concentration that are significant. So I need 3 significant digits in my pH, and the only thing that counts as a significant digit in pH are its decimal places. So if I have 3 total sig-digs in my concentration, I need 3 decimal places in my pH. So 13.079 would be the answer for that question. Now again, if you instead have a weak bases again are things like ammonia and your anions, with the exception of those conjugate bases of the strong acids. Okay? Now you may be given a compound. Let's say you have Na2CO3 and you're asked to find the pH of that compound. You need to think about again what that compound would actually split into once you put it in water. Now your cation, the sodium ion, is nothing. The only cation that is ever anything is the NH4 ion. The NH4 ion is a weak acid. Okay? But otherwise, you have an anion coming out of your ionic compound, and that anion is going to be your weak base. Okay? So they do not, I don't like the word dissociate, we should use the word react, because weak bases react with water, but they don't fully react with water. Okay, it's only a slight reaction. Now remember, if I were to write the KB expression for this, a base is something that accepts a hydrogen. A weak base is something that accepts a hydrogen when it reacts with water. So taking the hydrogen away from water, this weak base gains a hydrogen to become a base with the hydrogen ion now, and the water is left as hydroxide. Like we looked at yesterday with weak acids, if I were to now write an equilibrium table, an ice table, we omit the water because it's a liquid. I have an initial concentration of my weak base. I'm just going to put concentration of weak base, whatever the question gives you. I have no products to start. My weak base is going to go down by a small amount because it's barely ionizing. This reaction is barely happening. This is going to go up by a small amount, and this is going to go up by a small amount. So at equilibrium, my weak base is going to be the weak base minus whatever that small change is. My conjugate acid of my base that gained the hydrogen is going to be X, and the hydroxide ion is going to be X. So if I put this into my KB expression, it's going to be X times X over concentration of the weak base minus X. But your KB values are all going to be really, really, really small. So we can always use the approximation method here and cancel that out. Okay? Simplifying this, it would be X squared over the concentration of the weak base. Now, X again, like yesterday, is the concentration of my hydroxide ion. Once I solve for X, that is the hydroxide ion. So if I put this into the formula and get one formula for KB, it can be hydroxide replaced with X, because that's what the hydroxide equals. It's squared because X is squared, divided by the concentration of the weak base. Okay? So I can rearrange this formula, which we'll look at in a minute, to solve for the concentration of hydroxide ions for my weak base in solution. Now, before we get on to that, we're going to look at KB again, because KB is not given on the data booklet. But we know that Ka times KB equals KW. So if you're ever looking for the KB of something, you're going to take the KW and divide by the KA written right beside that base. So let's say we're doing SO4 2 minus. If I go back to that data booklet page and we look for SO4 2 minus on the base side, right? This is my base side. There's SO4 2 minus. That is the Ka of the conjugate acid, which is HSO4 negative. So I take my Kw 1.0 times 10 to the negative 14 and divide by 1.0 times 10 to the negative 2. Okay, so if we go back to that slide, the answer we would get for Kb, make sure you bring this in brackets. This should be in brackets. You hit divide and then put all of that in brackets. You should get 1.0 times 10 to the negative 12. Okay? So here is a sample diploma question. What is the Kb of OCl? And OCl is a weaker base than what? So is the Kb 2.5 times 10 to the negative 7 or 4.0 times 10 to the negative 8? And then is it weaker than the acetate ion or the phosphate ion? Let's go back. Again, this is OCl. Let's go back on that chart and take a look at that again. Okay, OCl is right here. This is the Ka. So obviously that's not the Kb because I would take that value and divide it. Well, I take Kw and divide it by that value, 4.0 times 10 to the negative 8. Okay, and then it's asking, is it a weaker base than PO4 or, the acetate ion? Okay, remember this chart, very similar to the reduction chart in the last unit. The strongest acids at the top, the higher you go, the stronger it gets. Your bases are the strongest on the right-hand side on the bottom, okay? So that means OCl is weaker than PO4 3 minus. It's stronger than CH3COOH, okay? So if we go back to that question, we find that our answer is A. It is 2.5 times 10 to the negative 7. And it is weaker than phosphate. It's higher up than phosphate. Okay, so let's look at pH calculations now with a base. So as I mentioned, if we were to write Kb over again on that ice chart like we did, we can simplify it into Kb equals hydroxide ion squared divided by the concentration of the weak base. So if I want to solve for hydroxide ions, it's going to be square root Kb times the concentration of the weak base. So let's look at the following example. I have 15 mole per liter solution of NH3. What is NH3? That's my first step, identifying my compound. NH3 is a weak base. It is on the chart on the right-hand side under the bases, and it is weaker than hydroxide, hydroxide being the only strong base. So it is a weak base. So that means, all right, I'm going to start by finding the concentration of my hydroxide ions by taking Kb, which I'm going to find in a second, and multiplying by the concentration of this base, which I'm given in the question. My Kb is going to, again, come from 1.0 times 10 to the negative 14 divided by, I need to get my data booklet out, we have ammonia. So the ammonium ion, Ka, is 5.6 times 10 to the negative 10. Now, remember you are not rounding at any point in this question until your final answer. So when I do this calculation, I need to leave it unrounded. It's 1.78. I'm just going to write it here. 1.78, so on, a whole bunch of digits, times 10 to the negative 5. I am taking this answer and plugging it into this formula. So what you're going to do in your calculator is hit the square root button. You're actually going to open a bracket And then inside a second bracket, you're going to select your answer, close that bracket, open another bracket and put 15.0, close that bracket, then close the overall big bracket for the square root. So you should get a hydroxide ion concentration of 0.0163 so on moles per liter. Okay, again though, I am not rounding this. I'm going to take the negative log of this answer, unrounded, and this is going to give me a pOH value, right? Because it's hydroxide ion, so that gives us pOH. That is 1.786 so on, but I'm looking for pH. The question is asking me for the pH. So now I go 14 minus this answer. Okay, you can write it like that on paper even, but make sure you're using all those unrounded answers. Now I get an answer of 12.2139 so on. I have 3 digits in my concentration, but my Ka value that was used in the calculation only has 2 digits. So that is limiting how many digits my answer can have. Okay, the Ka is not a constant. It's a calculated value given to you in the data booklet. It has 2 digits, which means I can only have 2 decimal places in my answer. So my final answer is 12.21. Okay. Next, we have another sample diploma question where we are given a Kb expression, okay, letting us know this is a weak base. The cyanide ion is a weak base. It's producing hydroxide ions, and the Kb is given. Now, it is asking us to find the equilibrium concentration of the cyanide ions. Well, the cyanide ions are my weak base. And I know that my Kb formula is concentration of hydroxide ions squared over the concentration of my weak base. Okay? Cn is my weak base, so that is what I am looking for. I am looking to solve for the weak base concentration. So if I rearrange to solve for my weak base, which is my cyanide ion, okay, it's going to be hydroxide ion squared over Kb. Now, how am I going to get hydroxide ions? Because I don't have them and I'm not using Kb to find them because I'm trying to find the weak base. We are given the pH. Okay, now the pH is not very useful to us because we have hydroxide ions. So I'm going to convert that into a pOH. 14 minus the pH. So 14 minus 8.710 is 5.290. Okay. Now I can find the concentration of my hydroxide ion with the formula 10 to the negative pOH, which was 5.290. Remember though, do not round that answer. Especially with these pH calculations, if you round early, it really affects your results. So 5.128 so on times 10 to the negative 6. I'm going to put this into that formula up there. That is my concentration of hydroxide ion. I have to square it and then divide by the Kb, which is given right there. Okay, so if I were to write this out, my cyanide ion, which is my weak base, is the hydroxide ion unrounded times 10 to the negative 6 squared divided by my Kb, which is 1.61 times 10 to the negative 5. Okay, I'm using that unrounded answer though. I'm squaring it and then dividing by 1.61 times 10 to the negative 5 in brackets. You should get an answer of 1.63 times 10 to the negative 6. Sig digs, I have 3 sig digs in my KB. All the digits count as sig digs. And in my pH, the decimal places are the sig digs, which are 3. Both of these have 3 sig digs, so my answer can have 3 total digits for concentration as my sig digs. It is telling you also to record it to 3 sig digs, but just a reminder, it wants the values for A, B, C, and D. So the answer would then be 1636. Okay? And that is it. Oh, actually, I have one more slide. The last slide is just a summary of your formulas. These are all the formulas that we've looked at over the last few lessons dealing with acids and bases. So your acids, again, are hydrogen donating compounds. They don't have to be neutral either. It could be something like HSO3, which is actually something that is amphiprotic. It could act as an acid because it has a donatable hydrogen, or a base because it's an anion. And anions, ammonia, and ionic hydroxides are bases. So if you get something that is amphiprotic, meaning it could act as an acid or a base, it's going to give you a hint as to what to do. Usually it tells you that litmus paper was used. Let's say it says litmus paper turns red, then you're going to treat it as an acid. If it says litmus turns blue, then you're going to treat it as a base. Okay? So that is it for this lesson. Thank you very much for watching this video.